In the previous lecture, we have been discussing about the linearity property of a system, and we have been talking about the scaling and additive properties as well as the superposition property. Okay, so what we basically said was that a system is linear if a linear combination of the inputs produces a linear combination of the corresponding outputs. So what we have here is a linear combination of inputs represented as a new input x of t. Then the corresponding output of the linear system will be a linear combination of the corresponding outputs. For example, if x1 of t produces an output y1 of t separately, and when x2 of t is applied as input separately, it produces an output y2 of t, and so on. Now if we make a linear combination of these input signals, then the output of the system will be a linear combination of the individual outputs. So x1 of t produced y1 of t, x2 of t produced y2 of t. A linear combination of the inputs is producing an output which is a linear combination of the corresponding outputs, which is a1 y1 of t plus a2 y2 of t. So a system which satisfies these properties, which are the scaling property or homogeneity property and the additive property, together we call this as the superposition property. Okay, if this condition is satisfied, we say that the system is a linear system. Okay, a linear combination of inputs produces a linear combination of the corresponding output signals. That is what we call as a linear system. If this condition is not satisfied, then the system is said to be a non-linear system. And generally these values a1, a2, a3 are complex numbers. So this relationship should satisfy for these scaling parameters a1, a2, up to an. Whether they are real numbers or complex numbers, it should still be satisfied. Only then we say that the system is linear. But for much of this course, we will be dealing with only the scaling parameters, which are real numbers. Okay, but the general rule is that it should satisfy, this property should be satisfied for these scaling parameters, which are complex numbers as well. Now, first consequence of the superposition property is that a linear system whose input is 0 will produce an output which is also equal to 0. Okay, that is called as a property where a 0 input produces a 0 output. We cannot have an output which is non-zero when the input is 0. Okay, that is the first consequence of a system being linear. What that means is, if our input signal x of n or x of t, right, depending on whether it's discrete time or continuous time. So if x of n is, let me write it. If x of n equal to 0 for all n, then y of n is also equal to 0 for all n. Or in continuous time, we can write this as x of t. Okay, if x of t equals 0 for all t, then the output y of t is also equal to 0 for all t. Okay, this is the first consequence of a system being linear, and it applies directly from the superposition equation. Okay, so if we have any signal which is 0 for all time, that means all the individual components are 0. That's when x of t is 0 for all t. Then the corresponding output y of t will also be equal to 0 for all t, because when x1 of t is 0, we'll get y1 of t which is 0. When x2 of t is 0, we get y2 of t is 0. So all of these will add up to simply give y of t which is equal to 0 when x of t is 0. That is what we mean by that. Okay, so the first consequence of this of a system being linear is that a 0 input will produce a 0 output for all time. And that applies for both the discrete case as well as the continuous time case. Now let us consider this system which has an input-output relationship given as y of t equals t times x of t. And this is the same system that we saw in the example for stability, and we showed that this system is an unstable system. It is not a stable system because when the input x of t is a constant, let's say x of t equal to 1, y of t will be equal to t. That means it keeps growing with time. So we saw that this is an unstable system. We want to check whether the system is a linear system or not. Okay, and to check whether this is a linear system or not, let's say consider an input x1 of t. Okay, so with input x1 of t, the output is y1 of t, right? Y1 of t, and that will be equal to t times x1 of t. Okay, so that's our input x1 of t producing an output y1 of t equal to t times x1 of t. Similarly, with input x2 of t, the corresponding output, we can denote that as y2 of t. That will be t times x2 of t. Now, if we have a linear combination of these inputs, that is x1 of t and x2 of t, then the corresponding output should also be a linear combination of y1 of t and y2 of t. If we can show that this condition satisfies, then we can say that the system is linear. Otherwise, it is not linear. So now we have defined x3 of t, a new signal x3 of t, which is a linear combination of our original signals x1 of t and x2 of t. So x3 of t is defined as a times x1 of t plus b times x2 of t. That is, x1 of t is scaled by a factor a and added to x2 of t, which is scaled by a factor b. So x3 of t is basically a linear combination of x1 of t and x2 of t. Now, when x3 of t is our input, we need to show that y3 of t, the corresponding output, is a linear combination of y1 of t and y2 of t. If that can be proved, then the system is linear. That is, this system is linear. Otherwise, it is a non-linear system. So let's see, with input x3 of t, it should give us an output y3 of t. It gives an output y3 of t, which is equal to t times x3 of t, right? It is t times x3 of t, because that's the input-output relationship. Y of t is t times x of t. So when the input is x3 of t, the corresponding output y3 of t is t times x3 of t. But we have now defined x3 of t as a linear combination of x1 of t and x2 of t. So that is t times x3 of t, which is a x1 of t plus b x2 of t. So we can write this y3 of t, that is y3 of t, can now be written as a t x1 of t plus b t x2 of t, which is equal to a times t x1 of t, right? T x1 of t is nothing but y1 of t, and t times x2 of t is y2 of t from here. So it is a y1 of t plus b y2 of t. So a y1 of t plus b y2 of t. So we see that when the input is a linear combination of the previous inputs or the other inputs x1 of x2 and x2, then the corresponding output is a linear combination of the outputs y1 of t and y2 of t. So we had a single input x1 of t that produced y1 of t, another input x2 of t produced y2 of t, and when we had a third input x3 of t, which is a linear combination of x1 of t and x2 of t, the corresponding output is a linear combination of the outputs y1 of t and y2 of t. So we see it's a y1 of t plus b y2 of t. So this particular system here is a linear system. So we can conclude that this system here is a linear system. Right? So basically, it satisfies the superposition theorem. When the input is a linear combination of some other inputs, then the corresponding output is also a linear combination of the corresponding outputs of those other inputs, right? So we say that this system is a linear system. So similarly, we'll do one more example of a case where the system is a non-linear system. So now let us consider the second example where the input-output relationship is given as y of t. The output is equal to the square of the input. So y of t is equal to x square of t. So in this case, to check linearity, let's consider an input x1 of t produces an output y1 of t, which is equal to x1 square of t. Similarly, an input x2 of t produces an output y2 of t, which is going to be x2 square of t. Okay. Now, if we have a third input x3 of t, which is a linear combination of x1 and x2 of t, then let's see what happens to the corresponding output. So consider x3 of t to be equal to a times x1 of t. We don't want to write that a1, just a is enough because we're using a and b, right? A times x1 of t plus b times x2 of t. So if x3 of t is a linear combination of x1 of t and x2 of t, we want to find out what will be the corresponding output signal. So then the corresponding output, y3 of t is going to be x3 square of t. So y3 of t is equal to x3 square of t, but x3 of t is a linear combination of x1 and x2, so that's equal to ax1 of t plus b x2 of t, the whole square. It's the square of this, right? That's x3 square of t. So this is like a plus b the whole square form. So we can write that as a square x1 square of t plus b square x2 square of t plus 2 times ab, right? That's 2ab x1 of t into x2 of t. So y3 of t, we need to show that it is going to be a linear combination of y1 of t and y2 of t. And if we can show that that is the case, then we can say that this system is a linear system. So what we notice is that this x1 square of t is nothing but y1 of t, x2 square of t is nothing but y2 of t. So we can write this as a square y1 of t plus b square y2 of t plus 2ab x1 of t into x2 of t. Okay, so again, we need to verify that this is linear or not. We need to show that for some input signal x1 of t and x2 of t, and for some constants a and b, we get a relationship for y3 of t which does not satisfy a linear combination of y1 and y2 of t. Okay, let's prove that now. Already we can see from this form, right? If this was linear, then y3 of t, it should have been a times y1 of t plus b times y2 of t. But that is not the case. We have an extra term here, and plus it's instead of a times y1 of t, it's a square times y1 of t and b square times y2 of t. So if this were linear, then y3 of t should have been a y1 of t plus b y2 of t. That's it, and without this additional term as well. but this equation is not satisfying this condition. So we can already say that this is a non-linear system, but we can also verify this by choosing some values for a and b and some values for x1 of t and x2 of t. So clearly we see that this is already non-linear, but we will also prove it with some arbitrary input signals. Okay, so let's write, since y3 of t is not equal to a times y1 of t plus b times y2 of t, this is not linear. So it implies that it's non-linear system. Now we can verify this by taking some arbitrary input. So let's say we give some input values, we define what is x1 of t and x2 of t, and also give some values to a and b, and we'll keep these inputs and constants as we'll choose them as some simple values. So let's say we choose a equal to 2 and b equal to 0. Okay, that's the choice of a and b, and let's choose x1 of t to be equal to 1. It's a constant. Okay, it's for all time, it's equal to 1. And x2 of t, let's choose x2 of t as 0. Okay, that is x2 of t does not exist. Okay, it is equal to 0 for all time. Now in this case we will see what is the x3 of t. So in this case, x3 of t, which is a times x1 of t plus b times x2 of t, is b is 0 and x2 of t is also 0. So we simply end up getting a times x1 of t, which is simply x3 of t, is equal to 2. Now the corresponding output y3 of t will be x3 square of t, which is equal to 2 square, which is 4. So y3 of t is equal to 4 for all values of time, when the input x3 of t is 2 for all values of time. Okay, so when we have these particular values for x1 of t and x2 of t, we get this y3 of t to be equal to 4. Now if this system is linear, then the condition that must be satisfied, okay, for linearity, y3 of t should be a times y1 of t plus b times y2 of t. So that is what we are trying to say here. Now what is y1 of t? When the input is x1 of t, y1 of t is y1 of t is t times x1 square of t, right? And when the input is x2 of t, the output y2 of t is 0, because x2 of t is 0. And we said previously at the beginning of this lecture that a linear system satisfies the condition of 0 input producing a 0 output. So if the input x2 of t is 0, the corresponding output y2 of t is also 0. So the output corresponding to x2 of t, which is y2 of t, is 0. So that will simply be a times y1 of t. So because b is also 0, right? B is 0. So that simply becomes a times y1 of t. A is equal to 2. So that's 2 times y1 of t, which is equal to 2 times x1 square of t, right? So that's x1 of t the whole square, or x1 square of t, right? So what is x1 of t here? x1 of t is equal to 1 for all time. So we have chosen x1 of t as 1, right? So that becomes 2 times 1 square, which is equal to 2. So we see that y3 of t, which is actually 4, does not satisfy the linear combination of y1 of t and y2 of t. It is not equal to a times y1 of t plus b times y2 of t. So 4 is not equal to 2, because if this condition was satisfied, then this answer should also have been 4. So we see that y3 of t is not equal to a y1 of t plus b y2 of t. So therefore it is non-linear. So since y3 of t is not equal to a times y1 of t plus b times y2 of t, that is 4 is not equal to 2, the system, so it implies that, let me leave some space there, so 4 is not equal to 2, so that implies that this system y of t, which is equal to x square of t, is non-linear. Okay, so we have seen this example of a non-linear system here, and previously you have seen an example of a system which is linear as well. So this system here, which we had tx of t, it is an unstable system, but it is a linear system. Here we have a system x square of t, and if you recall, this is the same example which you used to show a non-invertible system, right? Because x square, when the input is -2, the output is +4, and then when the input is 2, the output is also +4. So there are multiple inputs leading to the same output, so we cannot have an inverse. We saw this example a couple of lectures back, right? So this system is a non-invertible system, but and also it's a non-linear system. So we saw this example when we talked about the invertibility property of systems, okay? And we saw that this is a non-invertible system, and today we have also seen that this is a non-linear system as well. So basically, this is a procedure we are going to follow to check whether a system is linear or not. You'll just take any arbitrary signal x1 of t and x2 of t and take the corresponding output signals. Then we'll produce a third signal, which is a linear combination of the first two signals, and prove that or check that whether the corresponding output of the third signal is a linear combination of the corresponding inputs y1 of t and y2 of t, so corresponding outputs y1 of t and y2 of t. If this condition is satisfied, then we will say it's linear, otherwise it's non-linear. Okay, in this case, it is the output y3 of t is not a linear combination of y1 of t and y2 of t, therefore non-linear. And in the previous example that we saw, we proved that when the input is a linear combination of x1 and x2 of t, then the corresponding output is also a linear combination of y1 of t and y2 of t. Okay, so therefore we said that this is a linear system. Okay, so we have seen these examples of linear systems and how to check linearity of systems. Basically, it should satisfy the superposition theorem to qualify as a linear system. I also mentioned earlier that for a system to be linear, it should satisfy the superposition property even for complex values of a and b, right? Not just for real numbers, but we can have this a and b as complex numbers as well. So in that case, we'll see what happens, and we'll take a specific example of a system and check whether it is a linear system or not. Basically, it has to satisfy the homogeneity property, the additive property, or together we call it as the superposition property. And if both these properties are satisfied, even for complex values of a and b, then we will say that the system is a linear system, otherwise it's a non-linear system. And similarly, we can have the signals themselves, okay, x1 of t and x2 of t, to be complex as well. So there's no restriction that the signals as well as the scaling factors should be real numbers. We can have complex scaling factors as well as complex signals, and in general, the superposition theorem should be, or property of superposition should be satisfied whether our scaling factors and the input signals are real or complex. So it should be satisfied for all the cases, but most of the times in this course we'll be restricted to real signals and real scaling factors. But I just want to illustrate to you with complex signals as well, where a signal has a real part and an imaginary part, and I'm sure you're familiar with complex numbers. And if not, I recommend that you revise some basic concepts of complex numbers which you are expected to know. So if we have a system which is dealing with complex signals. Okay, so I've shown here the input signals x1 of n and x2 of n are complex signals. It has a real part and an imaginary part, a plus j b sort of thing, right? And the input-output relationship of the system is such that if we give a complex signal, we want to extract only the real part and ignore the imaginary part. So this system, when it takes a complex input signal, at the output it will produce only the real part. It will ignore the imaginary part. For example, that's our input-output relationship. So we define the system which has an input-output relationship as y of n is equal to the real part of x of n. So whatever complex input that we give as input to the system, the output is the real part of the complex input. So when we have the complex signal x1 of n as the input, then the corresponding output y1 of n is the real part of x1 of n, which is this r1 of n, which is equal to r1 of n. Similarly, when the input is x2 of n, then the corresponding output y2 of n is going to be the real part of x2 of n, which is r2 of n. Now, we want to check the linearity of the system, okay, which has an input-output relationship given by this. So we first check the superposition theorem, where x3 of t is going to be a linear combination of x1 and x2 of n. Okay, so and for simplicity, I've just taken these scaling factors a and b as 1. Okay, so a equal to 1 and b equal to 1. So x3 of n is basically x1 of n plus x2 of n. So that means I've chosen this a and b to be real numbers. Okay, the signals are complex signals, but the scaling factors are real numbers. Okay, in this case we will check whether y3 of n, which is the output to x3 of n, is a linear combination of y1 of n and y2 of n or not. So let's see this. So the corresponding y3 of n, so y3 of n is going to be the real part of x3 of n. So real part of x3 of n, which is equal to what is the real part of x3 of n? It is r1 of n plus r2 of n. That's the real part, and whatever is with the j, that's the imaginary part. So the real part of x3 of n is r1 of n plus r2 of n. So that's r1 of n plus r2 of n. But what is r1 of n? It is y1 of n. And what is r2 of n? That is equal to y2 of n. So that's equal to y1 of n plus y2 of n. So for constants, for the scaling factors which are real, this is a and b, any number, in this case it's 1 and 1, so we get the output as a times y1 of n plus b times y2 of n, which is 1 times y1 of n plus 1 times y2 of n. So it is linear in this case. But the condition for linearity is that it must satisfy this property for even complex values of a and b. So if we choose some complex number for this scaling factor a or b, then even in that case it should satisfy the superposition theorem. So we see clearly that the additive property is satisfied as well as the scaling property is satisfied when this a and b are real numbers. So let's check what happens if either of these is a complex number. So we see here that the additive property is satisfied when this a and b are real numbers. So let's see whether the scaling property is getting satisfied. So when our input is x1 of n, it produces an output y1 of n, which is equal to the real part of x1 of n. And what is the real part of x1 of n? That is r1 of n. Okay, so that is r1 of n. Okay, now if I had some scaling factor here, so if I give an input a times x1 of n, then the corresponding output should be, okay, if I call this as y2 of n, should be a times y1 of n. So when the input is scaled by some scaling factor a, then the output, the new output y2 of n, should be a scaled version of the original output y1 of n, which has the same scaling factor as a. Now let's check when a is complex. So when a is complex means with a as a complex number. So when you say complex number, it's like w plus j, let's say, let me use some variable which is not clashing with any of these variables that we have used there. W plus j times, let's call it m, okay? So we have this real part of the complex number, okay, which is w, and the imaginary part is m, okay? Now we'll make this as 0 and this m is equal to 1. So in this case, a is equal to j, okay? The real part is 0 and the imaginary part is 1. So we have a equal to j. Now in this case, when a is equal to j, we need to check whether the scaling property is getting satisfied or not. Call this new input, okay, x2 of n, which is a scaled version of x1 of n, where the scaling factor is j, 0 plus j times 1, which is equal to j. So our new input x2 of n is j times x1 of n, and since x1 of n is equal to r1 of n plus j times s1 of n, right? So that will be j times r1 of n plus j times s1 of n, okay? So we have this as x2 of n. So when we multiply this j inside, we get j times r1 of n plus j into j is j square s1 of n, and we know that in complex numbers j square is equal to minus 1. So that becomes equal to minus s1 of n plus j times r1 of n. Now, when we give this as our input signal, which is having a scaling factor as a complex number, then what is the corresponding output? So when we have x2 of n as input, it gives an output y2 of n, which is the real part of x2 of n. The real part of x2 of n is minus s1 of n, okay, which is equal to the real part of x2 of n, because the input-output relationship for the system is y of n equals the real part of x of n. So when the input is x2 of n, which is j times x1 of n, we get the real part of x2 of n, which is equal to minus s1 of n, right? Which is equal to minus s1 of n. And minus s1 of n is not equal to r1 of n, which is y1 of n. So that means y2 of n is not a scaled version of y1 of n, okay? So what we see here is that, so therefore we say that, therefore y2 of n is not equal to a times y1 of n, okay? That means the scaling property is not satisfied in this case. So when this scaling factor is a complex number, we see that the homogeneity property is violated, and therefore this system is a non-linear system. So we say that homogeneity property of what we call as the scaling property property is not satisfied. Okay, when is this not satisfied? When the scaling factor a is a complex number. So in this case it is, so therefore we say that this system, so therefore the system y of n, which is equal to the which gives the output as the real part of the input x of n, okay, is non-linear. It's not a linear system, okay, because for linearity it must satisfy the condition that a linear combination of the inputs produces a linear combination of the outputs, even when the scaling factors are complex. But here when the scaling factor is complex, it does not satisfy the property, and therefore it is a non-linear system. We clearly see that y2 of n, okay, y2 of n that we have here, which is equal to minus s1 of n, is not equal to a times r1 of n, okay. If that is j r1 of n, that is when it will be a times y1 of n. So that condition is not satisfied, and therefore this system which has this input-output relationship is a non-linear system, because it is not satisfying the homogeneity property when the scaling factor is complex. Let us now consider a third example of a system, and we will check whether this system is linear or non-linear. And again, I want to highlight very quickly an important property of a linear system. And if you recall, in a linear system, zero input should produce a zero output, right? So if that property is violated, automatically it is going to be a non-linear system. So let us take the system whose input-output relationship is given as y of n equals some constant times x of n, that is 2, the constant is 2, so 2 times x of n plus another constant 3, okay. So we have this system with input-output relationship given as this. Now as soon as we see this equation, this input-output relationship, we can deduce that this is a non-linear system, because when the input x of n is 0, what is the output? When x of n is 0 for all values of n, so 2 times 0 plus 3, the output is a constant value of 3. So it violates the 0 input, 0 output rule of a linear system, right? So as soon as we see that it has a non-zero output when the input is 0, we see that we can say that this system is a non-linear system, okay. So when x of n is equal to 0 for all n, we get y of n equals 3 for all n, right? So we are getting a constant output of 3 even when the input is 0 for all values of n. So this violates the 0 input 0 output rule for linearity, okay. So this violates the 0 input produces 0 output rule. So therefore a rule for linear systems, okay, for linear systems. So therefore this system is non-linear. Okay, basically what we're trying to do here is I'm trying to show you multiple ways of which in which we can identify whether a system is linear or not. So if we can show that a system with a 0 input produces a non-zero output, we can immediately say that this system is a non-linear system. Or we can go by the usual procedure. So our usual procedure is we'll take some x1 of n and another x2 of n, and then we'll make a linear combination of that x1 and x2 of n, and see that the corresponding output is a linear combination of the corresponding outputs as well, right? So let's say another way of proving that it is non-linear is another way is consider x1 of n as an input. So when the input is x1 of n, it produces an output which we will call as y1 of n, which is 2 times x1 of n plus 3. Similarly, if we had another signal x2 of n, we get a corresponding output y2 of n, which will be 2 times x2 of n plus 3. And now if we make a linear combination of these two inputs, so suppose x3 of n, x3 of n is a linear combination of x1 and x2, that is a times x1 of n plus b times x2 of n. Okay, so suppose we have x3 of n given as this, then what is the corresponding y3 of n? Then y3 of n, the corresponding output to x3 of n, which is y3 of n, which will be 2 times x3 of n plus 3, right? So what is x3 of n now? x3 of n is ax1 of n plus bx2 of n. So we need to just substitute that. So we'll get 2 times a times x1 of n plus b times x2 of n plus 3. So which will be so we can write that as a into 2 x1 of n plus b into 2 x2 of n plus 3. Now, is this equal to a times y1 of n plus b times y2 of n, right? It's not. So when x3 of n is our input, and since x3 of n is a linear combination of x1 and x2 of n, we write it like this, and basically we now write it, want to take this 2 inside. Okay, it's a into 2 times x1 of n plus b into 2 times x2 of n plus this 3 is standing outside separately, right? Now we need to show that this is equal to or not equal to a times y1 of n plus b times y2 of n. So let's write a times y1 of n plus b times y2 of n and see whether it's equal to this. If it is equal to that, then we can say that this is linear. In this case, it's not going to be equal because we have already shown that it is a nonlinear system because it violates the 0 input 0 output rule. So now let's see what is the linear combination of the outputs. Okay, let's write a times y1 of n plus b times y2 of n which is equal to what is a times y1 of n? It will be, so we multiply y1 of n by a, so we have y1 of n over here, we multiply this whole thing with a, it will become a times 2 x1 of n plus a times 3, which is 3a, plus b times y2 of n, which will be b times 2 x2 of n plus b times 3, so which is 3b. Now clearly a y1 of n plus b y2 of n is not equal to this y3 of n. Okay, so this y3 of n is not a linear combination of y1 of n and y2 of n because this a times 2x1 of n is there, b 2x2 of n is there, but this 3a and 3b are terms which are not here. Okay, this is 3 plus 3, it will we have only a single 3 here, but here we have 3a plus 3b, right? So we see that y3 of n is not equal to a scaled a linear combination of y1 and y2 of n. Okay, so we therefore we say that y3 of n is not equal to a times y1 of n plus b times y2 of n. So therefore it's non-linear system. Okay, this is a second way in which we can show it is non-linear. So we have used the first property of whether a zero input produces a zero output or not, and we saw that a zero input in this case is producing a non-zero output, therefore it is non-linear. Or we followed the conventional method of creating an input which is a linear combination of some other inputs, and then showing that the output is a linear combination of the corresponding outputs. So here we have seen that y3 of n is not the same as a times y1 of n plus b times y2 of n. Okay, so clearly it is non-linear. And a third way is by choosing some arbitrary values for x1 of n and x2 of n. We can take some simple values for x1 and x2 and see whether it satisfies our conditions. So let us do the third method now. So our system is having an input-output relationship given as y of n is 2 times x of n plus 3. Now we'll take some input signal. Okay, it has to satisfy for some input-output relationship, some input-output signals or relationship. So we'll fix this x1 of n and x2 of n to be some signals. So let's consider our x1 of n to be a constant signal 2. In that case, the corresponding output y1 of n will be 2 times x1 of n plus 3 that is. So x1 of n is a constant for all n, that is equal to 2. So 2 times 2 plus 3 it will give us 7. And similarly we'll consider x2 of n as another signal which is constant, so we'll choose it as 3 as in the example in the book. And in that case the corresponding output y2 of n is 2 times x2 of n plus 3, which is going to be equal to 2 times 3, which is 6 plus 3, 9. Okay, so that will be equal to 9. So x1 of n equal to 2 produces an output y1 of n which is equal to 7. x2 of n equal to 3 when given as input to this system produces an output y2 of n which is equal to 9. So now let's make a linear combination of x1 and x2. So we'll just verify the additive property now. So let's consider our x3 of n to be x1 of n plus x2 of n. Since x1 of n is 2 and x2 of n is 3, so x3 of n is going to be a sum of these two, which is equal to 5, right? So that is basically going to be x1 of n is 2 plus x2 of n is 3, which is equal to 5. And therefore the corresponding output y3 of n is going to be 2 times x3 of n plus 3, which is equal to x3 of n is 5, which is 2 times 5 plus 3, so that's 10 plus 3 equals 13. Now when the input x1 of n equal to 2 is given to this system, it produces an output which is 7. When the input x2 of n is equal to 3, the output is 9. Now when we add the two inputs, then the corresponding output is 13, which is not equal to 7 plus 9. It is not equal to y1 of n plus y2 of n, right? When the input is x1 of n plus x2 of n, if the output is y1 of n plus y2 of n, then it is linear. Okay, So we see that y3 of n here, y3 of n is not equal to y1 of n plus y2 of n, because y3 of n that we have here is 13, and 13 is not equal to y1 of n, which is 7, plus y2 of n, which is 9. So that means 13 is not equal to 16, right? So therefore the system is non-linear. So therefore non-linear system. Okay, so we have seen one more method here of finding linearity or checking for linearity. Okay, so we can do it in a general way, or we can take the zero input case and see what is the output, and if for a zero input we get a non-zero output, we can say it's non-linear. Or we can use some simple signals for our inputs and then verify the relationship and prove the additive and homogeneity property of our system input-output relationship, and check whether the system is linear or non-linear. In this case, we find that it is non-linear, and we have done it with three methods. So we have done it first for zero input. When the input is zero, we get an output that is non-zero, so it violates the zero input zero output rule, and therefore from this we can say it's non-linear. Okay, sometimes it may not be, the input output relationship may not reveal certain things. Okay, in this case we are able to see it in three different forms, but sometimes we have to choose a specific form intuitively. We have to work out which is the best way to determine or prove our whether our system is linear or not linear. So in this case we are able to do it in all three ways. Okay, where we saw the zero input zero output rule, or we choose the linear combination of the inputs in a generic way and showed that the output is not a linear combination of the corresponding outputs. And in the third procedure, we chose some arbitrary values or signals, x1 of n and x2 of n. Okay, and we chose some simple signals like constants. So we said x1 of n is a constant 2, it's constant for all values of n, it has a value of 2. x2 is 3 for all values of n, and then we apply the additive property and show that when the inputs are added together, the outputs are not the corresponding added outputs. Okay, when for example, as I said earlier, when the input x1 of n is 2, the output y1 of n is 7. When the input x2 of n is 3, the corresponding output is 9. But when we add these two inputs, the corresponding outputs are not added. Okay, the output that we get from the system is not the sum of these individual outputs, y1 of n and y2 of n. Okay, because the output that we get here is 13, but the outputs added, y1 of n and y2 of n added together, that gives us 16. Okay, so that is not equal, 13 is not equal to 16, so we say this is a non-linear system. So to summarize, we have seen 6 properties of systems. I'm just going to write down all of them. The first property that we saw is the whether the system has memory or memoryless systems. Okay, so memory or memoryless. The second property is the invertibility. The third property of the systems that we saw is the causality. The fourth property that we saw is stability. The fifth property is time invariance. And the sixth property is linearity. Okay, so we have seen these 6 properties of systems, and we have also seen how to check whether a system satisfies all these properties or not, whether a system has memory or is it memoryless, whether a system is invertible or non-invertible, whether a system is causal or non-causal, whether a system is stable or unstable, whether a system is time invariance or time varying, or in other words, not time invariance, whether a system is linear or a non-linear system. Okay, now an important class of systems that we'll be studying in the next chapter is what is called as linear time invariant systems. So we'll be studying about linear time invariant systems. Okay, we call this as LTI systems. Okay, and much of our next chapter is going to be dealing with understanding LTI systems and analyzing LTI systems, and we will be using a lot of developing a lot of tools to analyze the behavior of LTI systems. Now, a system can be linear and be time varying. Okay, and that is not time invariant, or it can be time invariant and non-linear, but we are interested in systems which are satisfying both these properties, linear as well as time invariance. So that we call as linear time invariant systems. We could have systems like we saw earlier, a system in this example, one example that we came across where we had a system that was unstable, right? Which one was that? So here, this was a system which was unstable but linear. Okay, so it need not be that a system satisfies all these properties. Okay, this is a system which is unstable. That means for a bounded input, it can produce an unbounded output, but it is linear. So it is unstable but linear. And here we saw an example of a system which is non-invertible and non-linear. And in particular, what we are interested in analyzing is systems that are satisfying both the properties of time invariance as well as linearity, and we call such systems as linear time invariant systems. Okay, so that is going to be our discussion for the next few lectures. And as I said in the beginning of this lecture, and even at the end of last lecture, that moving forward we are going to speed up. Okay, because you are getting introduced to these topics for the first time. I've been going a bit slowly till now when we were dealing with signals as well as systems and their properties. But now we are going to use these concepts of the different types of signals and the properties of systems to analyze our subsequent topics, to study our subsequent topics. So we'll be using these concepts directly now. So I recommend that you revise the lectures up to now and come prepared for the future lectures, because I can't be repeating all these things again and again. Okay, I will directly be using the words causal, stable, invariant, linear, and you need to immediately make sense of these terms in your mind and understand what we mean by those terms. Okay, so we'll stop here for today and we'll continue in the next lecture.